Hey, welcome to the last presentation in this series on introducing statistics. And what have we got here? Statistics measuring the spread. So the spread of data. You might guess what that means and have a look around the screen. We're going to have a look now at the meaning of the spread of a distribution of data. So looking around, there's some various interesting histograms around here. And I think as you look at them, you might see that measuring the spread of data could be quite a difficult thing to do. Obviously, what we've been trying to do is, with a data set, try to explain to people any patterns that might be there. A large set of data can be confusing. A lot of numbers, a lot of measurements. The graphs help us. And then calculating statistics like the mean and the median, the mode, trying to indicate where the center of the data is helpful. And also now what we want to try and do is indicate to people how spread out the data set was, without them actually looking at lots and lots of numbers. So let's have a look around the screen. I guess we could say up here, we could measure the highest minus the lowest and get an idea of what the range of the data is, and that's one measure of spread. How would that work over here, though, for this one? Oh, it might be a bit misleading. There's not too much down here, is there? Maybe we should even actually exclude those values there as perhaps outliers. We'd have to look at how the data was collected. And up here, the spread of data. Oh, that's a fair range, isn't it? Highest minus lowest, and perhaps that gives a false impression because that's a skewed distribution. So can you see the difficulty of indicating to people with one value that we calculate of what the true spread of the data is? Here's another one. Look at this. Big range, but really most of the data set is in here. Are you getting the idea? And I'm trying to set you up for a discussion later on as the best measure of spread under all these circumstances. Here we have possible outliers, and again the range of data could be a bit of a problem in indicating what's really going on there, and so on. So I want you to formulate in your own mind as we go around the screen there, perhaps what might be a better measure of spread than just the highest minus the lowest. All right, so start thinking and let's have a look. And we want to work into this presentation also the idea of the answer to the question from the last presentation, which was when would you use the mean, the median, or the mode to measure the center of the distribution? And you can see with these distributions around the screen now that in some circumstances, one of those might be better than the others. So I wonder if you've thought of that since the last presentation. Anyway, come down and let's have a look at an easy one. Here's an easy one. This is a set of distributions, cumulative here, continuous distribution, and they're all symmetrical. So let's have a look at the range. Would that be a reasonable measure of the spread of these distributions? You can see that they are spread out in different ways here. The least spread would be A. The next smallest spread would be B, and then C is the largest spread of data in those three distributions. So the range is the largest minus the smallest value. So that would be a reasonable thing to say here. I would guess they're nice and symmetrical, and the data is therefore evenly spread from the highest to the lowest. So we might give the range a tick in that situation. What about this? Have you ever seen this before? The interquartile range. The upper quartile minus the lower quartile, sometimes called Q3 minus Q1. We'll have to discuss that in a minute. I'll give you a brief introduction to it in case you haven't heard of that before. But we know the mean and the median are right in the center there. We discussed that last time with a symmetrical distribution. But what if we divided up into quarters the rest of the distribution? So in other words, this would be Q3, the score which has a quarter of scores above it, and Q1, which has a quarter of scores below it. And let's just look at how the middle 50% of all scores are spread. Can you see that's not a bad idea, because in a skewed distribution you don't have the tendency to count too high or too low. Come back up the screen and let's just have a look back up there and have a look at some of these. Can you see that? Let's take this one on the top left here. The range is a bit of a false indication, but if we took the interquartile range, we would have the median would be somewhere here, bottom quarter, top quarter, and it would be indicating where the bulk of the data appears to lie. That middle 50% is not very spread. Can you see that idea? Let's do another one. Come down here to the bottom left and have a look here. The range is across that, but here the interquartile range is there. A bit of a difficulty here. Bimodal, isn't it? Really two modes there. So we've still got some problems. But let's think about that interquartile range as indicating where the middle 50% of the data set lie, and whether that could overcome some of the problems with the range, particularly with a skewed distribution. Well, let's keep working on this. Come down and let's look at some of these distributions again here. So the range here, oh, well, yes, not bad, symmetrical distribution, but there's not too much out there, is there? So if we quoted the range, people might think, it's pretty spread out, whereas if we divide into quarters, here's the median here, lower quartile somewhere there. We'll look how to do this properly later, and this would be a little bit off to the right there, to the left there. So the interquartile range would be much smaller than the range and would be indicating to people where that middle 50% is, and therefore it's not as spread as perhaps a range would give as an impression. Here, well, we just looked at that one, bimodal. The range is probably not a bad indication. The interquartile range ignores the fact that there are lots of scores here and there, so maybe we would stick to the range for that one. And we just discussed this. The range is a bit misleading because of the positive skewness in this distribution. Can you see that? You remember that now? There's basic symmetry, and these are the extra ones which are skewing away from symmetry, that distribution, and so that's positively skewed to the right there. And in this one, I think the interquartile range may be somewhere in there, would be relatively small, and would give a better impression that, hey, there's a lot of scores here, and they peter out, if you like, up the top end. Can you see our difficulty? And here again, look how the range would be affected here, but the interquartile range would be somewhere middle 50%, and that would give a good indication of what was going on there. Okay, so it's got a lot to do with the symmetry of a distribution. It's got a lot to do also with the tails of the distribution, how extended they are, like this one here. Okay, so we choose our measure, our statistic, to indicate our data set very carefully, as we do with the mean and the median. Okay, so here's the data set here, and let's do the median, find the quartiles exactly, and find the interquartile range. So let's put them all in order. So there are 15 when we put them in order. So the middle score is the 15 plus 1 on 2, which is 8, and the 8th score is 6. Now, here's how we define the upper and lower quartiles. So we've got the median as the middle point. We now take the bottom half and find its median. So the lower half and the upper half of the data set, and we want the median of this. So there are 7 scores, so it's the fourth one, that's 3, and 7 scores above, so it's the fourth one, that's an 8. And so the interquartile range, that middle 50% is 8, take 3 is 5. So that gives you an idea that the middle 50% span a distance of 5 units, 5 points of whatever this data set is measuring, and they don't give it here. Okay, so let's come down and have a look at another one. So for this data set, find the median, Q1 and Q3, and the interquartile range. And we're not bothering with the range for these for the moment, because we're already a bit suspicious of the range, aren't we, in terms of the indication of that data set. Once we are just talking about statistics, measures of tendency within the data set, and we've lost the original scores perhaps, and we just want to indicate to people what was going on. So put it all in order. Now we have actually 20 scores this time. So 20 plus 1 is 21 on 2, comes to 10.5. Of course, there is no 10.5 score, so it's halfway between the 10th and the 11th, and that is the 6th score. So counting in the 6th score is actually the value 6. So here it is in here. We've got the 10th and 11th score, sorry, is a value of 6. 6 plus 6 on 2 is 6. So we're halfway between those two scores there. All right, so here, since we have an even number of values down below here, we're going to just call this time the bottom half and the upper half. We won't exclude the median because it's going to make it easier for us just to split this into 2 equal halves like that. So here, the median of this set, of course, is halfway between those two middle scores, and they're both 4, and this middle here is halfway between 9 and 10, and so it's 9.5. Same idea. So the idea here is to split the data set into an upper and lower half, and then find the median of the lower half and the median of the upper half. And that's going to split it effectively into quartiles, isn't it? So the bottom quarter is below 4, the upper quarter is above 9.5. 9.5 take 4 is 5.5. So the interquartile range is 5.5. And here's an important note with statistics. Some computer packages calculate some of this stuff differently, as they do with things like outliers, which we don't talk about a lot in this basic course here. But yes, there are various ways of calculating these statistics. All right, but we're going to use this one. It's a very simple one for this particular course. Okay, are you ready to try some stuff for yourself? And again, I'd like you to try it by hand as we just have done there, but there's a big emphasis in this particular course of doing it with technology. So let's have a look over here to start. We've done this already in an earlier presentation. With the Casio calculator, you choose stat mode and go to list 1. So if you choose stat mode on the Casio, you get this window, and you're going to insert the data in list 1 for a start. And then if you push the arrow at the end of the window there and go to, so that's F6, and go to the window where you have graph at the end here, then you'll be in the right window, and you've got to choose calc, which is F2, and then 1 there. And up will come all the statistics you want. There are no frequency tables here, so you don't have to worry about entering the frequency in list 2. Remember that that is important if you have a group data set or a frequency table. So here we have it, and we can go down and see that there's the median and Q1 and Q3 are all listed there. So just scroll down, and so you can work out the range also, because you've got the max and the min. So the range can be worked out and the interquartile range can be worked out. And if you compare those for data sets, you would get a good impression of how the data sets were spread differently by comparing the range and the interquartile range. So the interesting point here is if a data set differs from another because it's got a large range, but the interquartile range is approximately the same, that's suggesting that one is a skewed distribution, isn't it? Got some scores petering off to the left or right, but the basic middle 50% is spread in a similar fashion. So start thinking about how we're calculating this and the implications that it might have in getting a picture of what the data set looks like. Anyway, down here we've got the TI. Let's do the same thing here. So you need to go to stat mode and then going to one var statistics, and then again in list one, and then we have this window, and we can then go to our statistics here. Okay, similar pattern. So we've got min and max, we've got Q3 minus Q1, and we've got the median in there as well. So very similar idea. We don't have the mode on the TI. All right, so let's get started. I want you to do a couple by hand, but big emphasis on the use of technology in this course. Okay, so we'll pause the presentation there. There's question 1, 2, 3. So I want you to have a go. And remember, the fully worked solutions are coming up further down, so you can toggle forward and do a question, check the answer, and then come back and do the next couple and so on. Let's go on now to question 4. There's only 4 of them in this particular set. And have a look at that one. Again, have a look at your solutions and check that you've done things correctly. All right, let's come down now and have a look at the solutions. So here we are. Question 1, I think we can only get A and B on. We'll have a look at C in a minute. So pause it, have a look at how that's set out, and try to do a similar setting out yourself. Okay, so here's C and D in that question 1. Okay, coming down, question 2. Question 2 there. Question 3. Let's see if we can get all that on the screen. Question 3 and part of 4. We'll have a look at 4 in a minute. And question 4. All of that. So, yes, how are you going? You might have to go back and study these carefully. Let's move on, because we've got another little measure of spread that you might not have seen before, and this can be very useful, particularly in symmetric distributions. And here's what it's called. It's called the variance and standard deviation of a distribution. Now, what we're going to start with is talking about the whole population, right, that we are measuring. And rarely do we measure the whole population of items, whether it be, lifetime of car motors or something like that. We usually take a sample and make some inference about the population, because it's too expensive and too time consuming to measure all the individuals in the population, whether they be people or items. So we are going to talk about this for a start, as if we are able to measure every member of the population. So we have continuous data here, and we've got the whole population again measured in these 3 distributions, A, B and C, and they have different spreads as before. And so here we are. We're going to consider a population with n values, where n is usually very large in a population, and we're going to designate them x1, x2, x3, etc., as we did before. And we're going to use that Greek letter mu to mean the population mean. Okay, and we saw this before. Greek letters are used usually for the statistics calculated on the whole population. Okay, so what's this? Hey, can you understand that? I've just prompted that there because I wondered if you remembered what these symbols meant from before. What are we doing here? Let's have a look. We're adding up, this is the sum, isn't it, from I is 1 to n, so it's adding up all the values of what though? Not xi, not the mean. This is not the mean. It's the sum of the value minus the mean. What would you describe that as? We're adding up all the, what would you say, deviations from the mean? How much scores differ from the mean, from the population mean? So we've gone to the population. We're trying to find, let's take the green one here. There's what? This might be x 152 or something. And we're trying to find the distance away from the mean. It's that value minus that. And then we're going to average it, aren't we? We're going to find the mean. So this expression is an attempt to find the average deviation of each score away from the mean. We're going to subtract the mean away from each score. Let's take the mate of x 152. What do I mean it's mate? Well, it's going to be a symmetrical position down here somewhere. So whatever that is, x 90 or something. Okay, so if we do it with x 90, it'll be x 90 minus the mean. Oh, that'll be negative because it's on the left side. The mean is actually bigger than x 90, and this was positive. Uh-oh, can you see the problem? If we did that with a symmetric distribution, all the ones on the higher side would be positive deviations. The ones on the negative side would be negative deviations, or on the left there, lower side, negative, and they would cancel out. This little formula would come to 0. Well, that's not going to work, but can you see the notion? What we're trying to do is to look at how scores vary away from the mean, particularly when the mean is in the central position there in a symmetric distribution. Well, this didn't work. Finding the average deviations, the ones higher will cancel out the ones lower in their deviations away from the middle point. You might have to play that back again and just see if you can work that out. We'll come and look at some examples in a minute. So that didn't work, but our desire is to measure here, up here, the variation or the variance of scores away from the mean. Let's play with it a little bit and see what we can come up with. Well, here's one here. Let's try this one. If we squared the deviations, that's not a bad trick, is it? Added up all the squares of the deviations and found their mean. What would happen? Squares, you know something about squares. A negative square, negative times a negative is a positive. And a positive times a positive is a positive. All those deviations on the left side, if we squared them, the square of that variation would be positive, and we could add them up. Okay, get the trick. So the trick here is square the deviations away from the mean, and we're going to average those, and we call this the variance of the data. We couldn't unfortunately do it in simple terms because they cancelled out. Just simply take the deviation of the score away from the mean and add them all up. But we got the squares, so we're going to use this little symbol here. It's a Greek letter again. This is the small Greek letter sigma. The big one is used for sum. So this is a little one, and we're going to call it sigma squared in recognition of the fact that we're dealing with the mean of the variation, the squares of the variations away from the mean. Getting complicated? You don't have to actually understand this very much in this course, but I think as budding young mathematicians, it's good to have a go and see if you can think about it. So mu is the mean of the population, and n is the number of data values like we've just said. So this is some measure of spread. It's the squares of all the deviations of the scores away from the mean and add the average of those. Here we are. Okay, we come down and you might say, well, I was a bit worried about using the squares because that gives a larger value, doesn't it? We've squared them all, so we didn't cancel out the positives with the negatives. But now, what would be a good thing to do? We want to know, on the average, how far away is the data set away from the mean? How spread from the mean is it? You keep that idea in mind as we develop this formula. So now, what about taking the square root of it? So that would be a reasonable measure of the deviation on the average of scores away from the mean. The square root of the average of their squares. Okay, so it's not perfect, is it? You can see the problem here. And we're going to call this the population standard deviation. And we've lost the square on sigma. So there it is. And there's the evolution of what looks to be a nasty looking formula, doesn't it? But not so if you unpack it. Okay, work hard, think hard here. The sum of the squares of the deviations so they don't cancel out, and we want to find the average or the mean of those, and then we're going to take the square root of it so we've got some single number which is a reasonable indication of the average deviation of each score away from the mean. And I want you to keep in mind this is generally most useful for symmetric distributions. Just see if you can think why that might be the case. Let's say this is highly positively skewed, all this up here. Okay, and our mean is, well, it's going to be off the median, isn't it, because of the effect of those scores. So the mean's going to be there. The median is going to be back here. And we're going to measure the spread of this distribution away from a mean which has already been distorted by this skewness. So how sensible is that? Isn't it giving too much weight to the skewness because we've moved the centre because of the skewness? Can you see the dilemma there? So consequently, I want you to think about using the standard deviation mainly in the case of nearly symmetric distributions. We'll be doing more of this in another presentation on inferential statistics coming up next. But think about that. That's not too hard. You don't have to think about it in this course if you don't want to. All you have to do is apply the formula, and even then, we're only going to do it with technology. You don't have to do it by hand. It's a complicated looking formula. Okay, but keep thinking. Down we go here. Let's have a look. So now I want to do something a little bit more relevant than that last one, because we have said throughout these little presentations on this basic approach to statistics that we usually use a sample. Why? Have a look at the diagram. Isn't that nice? Nicely coloured diagram there. Got that just for you. The population is usually too large to work with, and we usually use a sample to estimate what's going on in the whole population, because we can't afford, don't have the time, can't access all the individuals maybe in a population, whether they be car motors or volume of in drink cans or whatever, to actually find out what's going on there. We're going to use sampling techniques. We're not going to talk about sampling techniques in this course, but we try to do random sampling basically. That is to give every individual in the population an equal opportunity of being included in the sample, so the sample becomes a good estimate or a good picture of the population. So we need to go back now and say, well, if we had a sample, what would the variance, that's the mean of the squares of the deviations away from the mean, the sample means, because we haven't got the population mean, too hard to do it. And what would the standard deviation be of those scores? So we're going to do the formulas again now based on a sample. because we realise the population's too hard to measure. Come on down, and we're nearly at the end. I hope you're not getting too tired here. You might have to come back and have a look at this again a bit later on. So here's our little picture. This is what we're doing over here, and this is what we're going to get out of it. If we take a sample from a population, here we are, and there's the population. We use Greek letters for the actual proper values when we measure the whole population. We talk about its mean and its variance and its standard deviation. And in our sample, we'll use different symbols. You've seen this on the calculator, X bar, and we're going to use S squared for the variance and S for the standard deviation. And this is just to distinguish whether we're working with a statistic. A statistic is a value calculated to describe properties of a sample, or whether we're working with a parameter. Now, we've had this in the earlier presentation. You might have had it in earlier basic statistics courses. A parameter is where we're measuring the property of the whole population. Rarely done. Okay, you know, we do census in countries to see how many people there are and all that sort of thing, but it is rare that we measure every individual in a population. So the statistic is an estimate of what really is going on for the whole population, which is measured by a parameter. Okay, this course is basically descriptive, a little bit of inference, and we're going to be measuring the sample, not the whole population. So come on down and let's have a look. Here we are. This is a little bit of a spiel for later on, and this is called Statistical Inference. And I think the diagram says it all, doesn't it? Here we take a sample. I shouldn't really use that implication sign there, because that means that the statement here implies the statement there. Not really, there are no mathematical statements. I'm using it to say from the sample calculation we can make some inference or some implications about what the population would be like. And it's called exactly that. Language in mathematics is very, very simple. It uses the English language in a non-confusing and a consistent way. So from statistics, statistical calculations, we can infer something about the whole population. Okay, and that is, we're going to estimate the parameters of the population, the properties like the mean, median, mode, from the statistics calculated based on our sample. So statistics infer something about the value of parameters. All right, you don't have to know a lot of that language, but some of you will be going on with maths, and it's good to have a sound foundation that can be built upon. All right, here we go. We have these summaries now. So our formula for the sample variance is S squared, and for the sample standard deviation, remember we're taking the square root of it in an attempt to measure the average deviation of single scores away from the mean. All right, so you don't have to do that calculation in this course, straight into technology, but it is very important, I think, to know what you're doing and the limitations of it. So into technology now, here we have the Casio and the TI, and these are the values we're trying to pluck out. Now, again, in this course, we're not going to make attempts at measuring a whole population. Generally, we'll be doing a sample, and obviously, we've learned already how to get to this window from the Casio and the TI, and the values we want are here. Sx, that's the population parameter, as we said before. You may, in some instances, have a small population of maybe 50 scores or something, in which case you will use sigma x, but basically our work will be on data sets which represent samples taken from a larger population. Just watch the TI here. It's got it in a different order, SX on top and sigma x underneath it. Just remember the Greek letters, okay, mu, sigma squared and sigma are for the parameters, are for population values, population parameters, and that means if you want a sample one, you don't use those, you use the standard deviation as S from S in the English language, S for standard deviation. All right, clear enough? Oh, you might have to go back and have a look at this, talk to your teacher, talk to classmates about that, and there's a lot of stuff to think about. Okay, so here's an example. Let's have a look at this. Supermarket manager is interested in the number of items customers buy. She takes a random sample. So there's only 6 customers. Discrete data, it's a number of items that people buy. You can't buy half an item. Find the mean of the sample, and so here you're going to add them all up and divide by how many there are. Pretty basic here. Find the sample standard deviation using, there's, they give you the formula, and using technology. Well, let's go through this because it is interesting to see how painful it is. Here are the scores. We take away the mean, okay, that's a sample mean because we can't measure the whole population. And then we've got to square it, add them all up, divide by n, take 1, which is 5, then take the square root. Quite a bit of work if you have a large sample. So this is generally not what we will be doing in this course. Here it is down here. We're going to use technology. So they're given 2 Casios here. They're the same, the later model, and the TI here. Don't forget now, with this, all you have to do to use this is to go into stat mode in each case, enter the data into list 1. No list 2 entry, it'll be the default frequency 1. Because they are each occurring only once. Watch out if they do give you a frequency table that you have to put that frequency into list 2 and then just proceed as before. Okay, as we've done in the earlier presentations. Got it? Well, let's have a look and see how good you are. Have a go here and then I'll give you a rest. This is the last set in this particular presentation. So here we go. Consider the sample data there. Find the mean. So try it by hand. Have a go by hand just for this little one, but then quickly revert to the calculator. Look at this little figure here. She's saying what we've been pushing quite a bit with this statistical inference. The sample standard deviation is an approximation of the standard deviation for the whole population. And the standard deviation for the whole population would be called the parameter, representing the population. All right, so here we go. Pause presentation, 3 questions there. Do one and do it with technology as well, and then toggle forward and find the solutions down below. All right, let's move down to question 4. 4 and 5, let's put those 2 up there for the minute. And obviously we're getting into bigger data sets, so we're going to use technology here for the bigger ones. And let's do question 6 now. And we'll bring up the last few here, 6, 7 and 8. And then 9 and 10. And that's all I've got for you there. So pause that, have a go, and let's go and look at the solutions now. Coming down, we have question 1 and 2. Question 3. Question 4 now. I'll just get question 4 on. Question 5. Question 6 done in a table. You probably didn't do that like that. Technology is okay for that one in this particular course. Question 7. And question 8, again, we'd use technology there. Question 9. And question 10. Let's see if we can get it all on there. There's question 10. Well, I hope you've enjoyed these short presentations on basic statistics. Just keep in mind, we started off with descriptive statistics, just trying to describe the data set with graphing and with the centre and the spread. And then we've finally gotten on to the notion of statistical inference, where we take a sample, describe it, and try to get a picture from that of what the whole population would be like. Okay, so there's one final presentation in this area of basic statistics in this course, and I hope you'll look forward to seeing that. I'll catch you then. Cheers for now.